In this video, we're going to continue our force problems, and specifically we're going to focus on problems with tension, friction, and inclined planes. Okay, so here we have a problem where we want to find the tension in the three cables that are shown in this figure. So you have a cable connecting two boxes. We have a cable A, cable B, and cable C, and we want to find the tension. So with a problem like this where you have multiple forces, and really any force problem, you want to start off with a good free body diagram for all of the objects you're interested in. So I'll start with the block with weight 1. So if I draw the free body diagram, it has a tension force TB pulling up and to the right. There is a second tension force pulling up and to the left, TA. And I'll go ahead and put my x-axis. Okay, so I can write these angles. If this angle that this cable makes with the horizontal roof is 45 degrees, then it will also make an angle of 45 degrees with the horizontal that I've drawn down here. Likewise for tension in cable A. And then we also have a weight. We have the weight of the first box pointing down, and we also have tension in cable C. Okay, so tension is very important. That tension always pulls. Okay, you never have a rope that pushes. So anytime you have tension forces that are touching an object, a cable, a rope, a string, anything like this, cord, it's always going to be a force that is away. So when you draw your dot representing your object, your tension forces will always point away from the object. Okay? And then if we draw the free body diagram for weight 2, we have the weight going down, and the tension in C is now pulling up on the first weight that's on the bottom. Okay? Or I guess weight 2 that's on the bottom. So I'm going to start off working with the second weight, and I'm going to do that just by looking at my free body diagram. I only have two forces, and they're all along the y-axis, so that tells me that this problem is probably going to be much easier than doing Newton's second law with my first weight. And so I'm going to start by summing up the forces in the y direction, since that's all the forces on my bottom weight. So if I do that, I have a positive TC since it's pulling up, and a negative weight of the second block. So that's my net force in the y direction. I'm now going to set that equal to mass times acceleration in the y direction. But all of these objects are just sitting at rest. They're not moving. So that tells me my acceleration in the y direction is 0. And now I can solve for TC in terms of the weight of the bottom block. So if I just move W2 over, I find that the tension in cable C is equal to the weight of the bottom block, or 140 newtons. And this kind of makes sense. This cable is really, its only purpose is to support the weight that's below it, and since we need everything to cancel out, they have to be equal and opposite. So now I will move on to the top weight, weight 1, and I'm going to sum up the forces in the x direction first. Okay. So if I do that, I have the tension in cable B, and if I want the x component on my free body diagram is adjacent to this angle. So adjacent means I want to use cosine of this angle to pull out the component. And then the tension in cable A is to the left, so it's going to be minus. And it is also, the x component of TA is also adjacent, so that's going to be cosine of 30 degrees. And that is also going to equal 0 because the acceleration in the x direction is 0. So now what I need to do is solve for either TB or TA, either one, in terms of the other, and then I'll use that later on. Okay, so I'm going to solve for TB since TA has a minus sign in front of it, and I can just move it over and make it positive. So that will give me TB is equal to TA cosine 30 degrees, and then I'm going to divide by my cosine 45 to get TB by itself. And so cosine of 30 over cosine of 45, that's just a number. Okay, sine and cosine of an angle just gives you some decimal that tells you some component of your force. And so this is just a number, and when I plug it in my calculator, I get 1.225 times TA. Okay, so this tells us how TB and TA are related, and that will help us solve for the tension. So now I'm going to move on to the y component, my y equation. So here I have all four forces that have y components. So I'm going to start with my positive ones first. So TB and TA both have positive y components. So TB, and once I find which trig function goes with the x component, I immediately know the y component is the other trig function. So instead of cosine, we have sine. Same for TA, it's going to be sine of 30 degrees. And then my weight and tension in cable C are negative. Okay, so I know this is minus 80 newtons for, or maybe I just write this as weight 1 minus TC for now. And just as I did in with weight 2, the acceleration is going to be 0, so I'm going to set all that equal to 0. Okay, so now I'm going to plug in, and I still have TB and TA in this equation, so I want to use what I just learned using my x equation to get this all in terms of either TA or TB. So everywhere I see TB, I'm going to substitute 1.225 TA. Okay, so instead of TB, I'm going to write 1.225 TA sine of 45 plus TA sine of 30. And then I'm going to go ahead and plug this in, minus 80 newtons for weight 1, and minus TC, we found that was equal to 140 newtons, or our bottom weight. And all of that is 0. And now all I need to do is isolate TA. So I'm going to factor out TA of these first two terms. 1.225 times sine of 45 degrees plus sine of 30 degrees. So I just factored that out of both of these. And then I'm going to move these two negative forces to the other side and add them together. So plus 80 and plus 140. That will give me 220 newtons on the other side. Okay, now all of this is just a number. So I just need to divide by it on both sides, and that will give me TA. So if I move that over and punch it in my calculator, I will get 161 newtons. Okay, so that gives me, I have TC, I have TA, and now I need to go back and find TB. So I can use this equation that I had before. TB equals 1.225 times TA, or 1.225 times 161 newtons, and that gives me the tension in TB as 197 newtons. So in this problem, we have a 50 kilogram wagon that is being pulled up a smooth ramp that is 30 degrees above the horizontal. The rope pulling the wagon makes an angle of 42 degrees above the ramp, and we want to find the tension in the rope if the wagon is pulled at a constant speed. So the first thing we want to do is make a free body diagram for our wagon. And since this wagon is moving on a ramp, we typically want to rotate our coordinates to make our forces align with our x and y directions, or our x and y coordinates. And so we're going to rotate our coordinates such that our y-axis is perpendicular to the surface, and our x-axis is along the ramp. And in this case, since this tension is going to pull the cart up the ramp, I'm going to make the motion in the positive x direction, or up the ramp. So your coordinate system is just a tool that you use, and so you should do what is most convenient and makes your math easier. So now I'm going to start drawing my forces. So the weight is always straight down toward the earth. The normal force is going to be perpendicular to my surface, so you have to be careful not to draw that straight up. And then this tension force is at 42 degrees above the ramp, or above my new x-axis. Okay. Now for my weight, I know that my weight is going to have the same angle as the ramp, because my weight used to align with my old y-axis, and since I rotated my y-axis 30 degrees with the ramp, the weight is now 30 degrees with my new y-axis. So this is something that if you don't know or you can't see it, you can memorize this. If you rotate your coordinates, your weight will always make the angle, an angle with the new y-axis that is equal to the angle of the ramp. Okay, so just looking at this, I can see that I have less forces with x components. So I'm going to start summing up the forces in the x direction. Okay, so might be easier. So Fx, the first force in the x direction is the x component of my tension, so Tx, and it is up the ramp, so it's positive. And then my weight has a negative x component, or an x component that is down the ramp. And I set this equal to mass times acceleration, except it told me that the cart was going to be pulled, or the wagon was going to be pulled at a constant speed. Constant speed means I'm not accelerating, I'm not speeding up or slowing down, so my acceleration is 0. Okay, now I just need to fill in my x and y, or my x component of tension, my x component of weight, using my right triangles. Okay, so if I look at the tension force, the x component is adjacent to this 42 degree angle, so the x component is going to be tension times cosine, so cosine is always adjacent, 42 degrees, minus the weight, and the x component of weight is opposite of this 30 degree angle. Opposite is always sine 30 degrees, and that's all equal to 0. And now I don't know exactly what the weight is in newtons, but I do know its mass in kilograms. So I'm going to rewrite my equation replacing weight with mass times gravitational acceleration. Okay, and now I know everything except my tension, so I'm going to solve for it. So if I do this, I get tension. I'm going to move mg sine of 30 to the other side, and then when I do that, I want to divide by cosine of 42 degrees to get tension by itself. And then when I plug all of this in my calculator, so 50 kilograms times 9.8 meters per second squared, and then my sine of 30 degrees over cosine of 42 degrees, I get a tension of 330 newtons. So in this next problem, we have a pendulum that hangs from the top of a box that is accelerated to the right at 2.5 meters per second squared. And we want to find the angle that the pendulum makes when it is deflected during this acceleration. Okay, so you probably know, if you've ever been in your car and you've had something hanging from the rearview mirror, if you step on your accelerator and you start to accelerate, something might bend closer towards you. It may bend in the opposite direction that you're accelerating, kind of like your car is trying to go out from under it. And so we want to see if we can't find this angle. So we want to start off by drawing a free body diagram of this pendulum. So it has a tension that is going up and to the right. Since we're accelerating to the right, we know it's going to be deflected to the left. So there's some tension along the pendulum. And then it has a weight that is going to be straight down toward the earth. And we know that this is the angle we're looking for, the angle the tension makes with the y-axis. Okay, so now I'm going to start by just summing up my forces. Okay, in Newton's laws, if you ever don't know what to do and you have a force problem, just start summing up the forces. So I'm going to begin by summing up the forces in the x direction. So in this case, if I just draw my xy coordinates on my free body diagram, the only force that has an x component is my tension. So it has an x component, and I'm going to set that equal to mass times the x component of acceleration. Now, the x component of tension is going to be, well, this angle. Both of these angles are now opposite, or these are called vertical angles. So this angle theta is equal to the angle made with the y-axis. So my x component is going to be opposite of this angle. So my x component will be t sine of theta, and that's going to equal mass times acceleration. Okay, and that's as far as I can go. I don't know the tension, I don't know the mass of this pendulum, and I don't know, oh, I know the acceleration, and I'm looking for the angle. Okay, so I have too many unknowns to solve for theta, so I'm going to start summing up the forces in the y direction. So I have the y component of tension, and now the weight is all in the negative y direction. And set that equal to mass times acceleration in the y direction. But here we're not accelerating up or down, so the acceleration is 0 in the y direction. The y component of this tension, we knew the x component was sine, so now this is going to be cosine of the angle I'm looking for. And since mass shows up in my x equation, I'm going to write the weight as mg, okay, hoping things might cancel out. And I'm going to set that equal to 0. Okay, so now I have two formulas with, or two equations with tension in it. So I want to solve for one of those and then substitute it into the other. So if I do this, if I solve this second equation for tension, I'm going to move mg over and then divide by cosine of theta to get tension by itself. And then I'm going to take this and plug it in to my first equation with tension. So everywhere I see t, I'm going to replace it with mg cosine theta. Okay? And so that gives me mg over cosine theta times sine theta, and that's equal to mass times acceleration in the x direction. So first, I can see my mass cancels out. That happens a lot in Newton law problems, so you should always look for it. And then I have a sine theta over cosine theta. So this is going to give me g times tangent of theta, since sine over cosine is tangent, equals the acceleration in the x direction. And now I can solve this for my angle, so I get tan theta equals ax divided by g. And taking the inverse tangent of both sides, theta equals tan inverse of 2.5 meters per second squared over 9.8 meters per second squared. And the angle that my pendulum makes is going to be 14.3 degrees. And one interesting thing to note is this didn't depend on the mass of the pendulum. It only depended on how fast I was accelerating. Okay, so a lot of things we find are independent of mass, and it's kind of interesting that no matter how heavy this pendulum is, it's going to be deflected at the same angle according to how much we accelerate. In this next problem, we have a 50 kilogram block that is sitting on a smooth ramp that is 35 degrees above horizontal. This block is connected by a rope and pulled by a second block hanging off of the ramp. How much should the second block weigh for both blocks to remain at rest? So, as with all Newton's second law problems or force problems, we want to start by drawing free body diagrams with all of our forces. So I'll start with mass 1. Since mass 1 is on the ramp, I'm going to draw it with a rotated coordinate system. So the normal force is going to be perpendicular to the ramp, and the weight is always straight down toward the earth. And the tension in this rope is always going to pull away from the object or up the ramp. Okay, so now I'm going to add my X and Y axes. And I'm actually going to put the X-axis going up the ramp since the first block is going to be pulled by the second block. Okay, so now I'll draw my second free body diagram. So this one's rather simple. I have just the second block being pulled up by this rope, and then its weight is pulling straight down. So we only have forces in the y direction. And now I'll start by doing Newton's second law. And I'm going to start with the second mass since there's only two forces. So it's a little bit simpler, and they're all in the y direction. So M2, sum up forces in y. If I do that, I get the tension that is pulling up minus the weight of the second block, and that's equal to mass times acceleration in the y direction. But we want to know how much the second block is going to weigh for them to remain at rest, so that means that it's not going to accelerate upwards. So this is 0. Okay, and then tension, I'm going to solve for it, is going to be minus m2g. So I'm going to plug in mg for the weight of the second block, and that's going to equal 0. And when I solve for tension, I'll just move this to the other side and get the tension is equal to the mass of the second block times gravitational acceleration, or the weight of the second block. Okay, and so there's nothing else I can do here, so I'm going to move on to the first block. I'll start with adding up the forces in the x direction. I'm going to do that. I will have tension. Okay, so this tension is going to be equal for both masses, since nothing is moving. So I have the tension minus the weight of the first block in the x direction. Okay, so I'll put my 30-degree angle here. Okay, and this is going to equal the mass of the first block times acceleration in the x direction. But again, since it's remaining at rest, that's going to be 0. Okay, so now again I'm going to plug in my x component of the weight. So weight 1, that's going to be m1 times g, and then to get the x component is opposite of this 30-degree angle, so opposite is always sine, so sine of 30 degrees. And that equals 0, and now I can solve for tension. T equals m1g times sine of 30 degrees. And so again, I have two equations for tension. I'm going to take my first one and plug it into my second one. So if I do this, I get m2g equal to m1g sine of 30 degrees. And since I have a g on both sides, I can divide both sides by g and get rid of that. And I want to find how much the mass of 2 needs to be, so m2 is going to equal m1 times sine of 30 degrees, or this is 50 kilograms times sine of 30 degrees. And so m2 needs to be 25 kilograms. And then if I wanted to find the weight of block 2, I would just do 25 kilograms times 9.8 meters per second squared. Okay? Next problem, a 4 kilogram block is at rest on a rough table with a coefficient of static friction of 0.45 and a coefficient of kinetic friction of 0.3. What is the minimum force needed to accelerate the block? And if this force is maintained, what will the acceleration of the block be? Okay, so first I'm going to draw a picture so I know what's going on. So this block is on a rough floor. So I usually draw some dashes to indicate that. And there's a force needed to accelerate this block. And so I'm going to start by drawing a free body diagram. So this block has a weight that is straight down, a normal force that is perpendicular to the surface or straight up, and we're going to push it to the right, so everything's moving in the positive x direction. And that means that friction is going to oppose our motion. So if we're going to push the box to the right, friction is going to be to the left. Okay, and at first we're going to consider static friction, since we're looking at the minimum force needed to get the block to accelerate or get it to move from rest. Okay, so I'll start by summing the forces in the y direction. So this is something I often do because I know when there's friction in a problem, friction depends on the normal force, and typically the normal force is in the y direction. So I go ahead and find out everything I need to know about the normal force right off the bat in the y equation. So if I sum up the forces in y, I get the positive normal force minus the weight of the block, and that's equal to ma but the block isn't accelerating through the floor or up off of the floor, so this acceleration is 0. And I'm going to plug in mg for the weight, use my formula for weight, and I get that the normal force is just mass times gravitational acceleration. Okay, now I can move on to the x component of the force. Okay, sum up the forces in the x direction, and I get this horizontal force that I'm applying to the right minus the force of static friction to the left. I'll set this equal to mass times acceleration in the x direction. And since I'm trying to accelerate the block, it hasn't quite moved yet, so my acceleration is going to be 0. And this is always true. Anytime you're using static friction, you're going to set the acceleration to be 0, because if you did start accelerating, then you would be using kinetic friction because now the block's moving. So if you're looking for anything involving static friction, or you have a static friction force, that tells you that your acceleration better be 0. Okay. So now I'm going to plug in my formula for static friction, our coefficient of static friction times the normal force, set that equal to 0. And now I can use what I learned about the normal force and summing up the forces in the y direction, and I get F minus mu s times mg is equal to 0. And this minimum force needed, I just move this to the other side, and I get 0.45 for my coefficient of static friction times 4 kilograms of the block times 9.8 meters per second squared. And this gives me a force of 17.64 newtons. Okay? So now, if I maintain this force and I keep this force, I want to know what the acceleration will be. So now I'm going to sum up the forces in the x direction, yet again. But now I'm going to have this force, and my static force of friction is going to turn into kinetic friction. So I get minus Fk, still to the left or in the opposite direction that the box is moving. And now my acceleration is no longer 0 because now it's moving due to this force. Okay? So again, I'm going to substitute mu k times the normal force for my friction force. Okay? And if I solve for the acceleration in the x direction, I need to divide by m on both sides, so I get F minus mu k, and for n I'm going to substitute mg since I know the mass of the block. Okay, and divide that by m. And if I plug this in, I get 17.64 newtons for my applied force from part A, minus coefficient of kinetic friction of 0.3 times 4 kilograms times 9.8 meters per second squared, all over 4 kilograms. And that will give me an acceleration of 1.47 meters per second squared. Next problem, after a shove, a book slides across the floor at a speed of 2.2 meters per second and comes to a stop after sliding a distance of 5.5 meters. Find the coefficient of kinetic friction. So I'm going to draw a picture, as I always like to do, of a block that slides across a rough floor because there is friction, so it's moving to the right. Draw a little velocity vector. And so first I want to draw a free body diagram. So I have a normal force that is perpendicular to the surface, a weight that is straight down, and there are no forces pushing this object. It's already been shoved and it's moving, sliding across the floor. And since it's moving, there is a force of kinetic friction that's fighting its motion. Since it's moving to the right, friction will be to the left. And so now that I have all of my forces, I'm going to start summing up the forces. So I'm going to start with the y direction. Again, I like to start with y when I have friction. So if I sum up the forces in the y direction, I have the normal force minus the weight, and that's going to equal mass times acceleration. But since the book is not moving through the floor or up off the floor, acceleration in the y direction is 0. And I'm going to substitute mg in for my weight. And when I solve, I get the normal force is equal to mass times gravitational acceleration. Okay, so now that I know my normal force, I can sum up the forces in the x direction. And all I have is the force of kinetic friction, so Fk, equals mass times the acceleration in the x direction. So if I substitute n for Fk, mu k times n, the normal force, and again take the normal force I found from the y equation, I get a mass in both sides of my equation, so that goes away. And if I want to find the coefficient of kinetic friction, I will need to find the acceleration. Okay, so I get mu k is equal to minus ax over g. Okay, so now I need to find the acceleration. Okay, so one thing to notice is my friction force is the only force acting in the x direction, and it depends on the coefficient of kinetic friction, which is a constant, times the normal force, which is also a constant. So all three of these are constants. And since kinetic friction gives me my net force in the x direction, if kinetic friction is constant, that means my net force is constant, and so my net acceleration in the x direction is constant. Therefore, I can use my kinematic equations for constant acceleration. So, since I'm starting off at a speed of 2.2 meters per second, that is my v naught. When I come to a stop, that tells me my velocity is 0. And I'm going to do that after sliding a distance of 5.5 meters. Okay, so I'm given all this information, and I don't have any information on time. So the kinematic equation I want to use is vx squared equals v naught x squared plus 2ax delta x. My final velocity is 0. And now if I solve for the acceleration, get minus v naught x squared over 2 delta x. So this is minus 2.2 meters per second all squared times 2 over 2 times 5.5 meters. And that gives me an acceleration of minus 0.97 meters per second squared. And now that I know this, I can plug it into my equation and solve for mu k. So I have minus 0.97. Mu k should be positive, so it's a good thing I got a negative number, or a deceleration, over 9.8 meters per second squared. And this gives me a coefficient of kinetic friction of 0.1. In the next problem, you have a large box laying on a wooden plank, and when the plank is raised to an angle of 40 degrees, the box begins to slide, and we want to find the coefficient of static friction between the box and the plank. So we start off with our box on a plank, and then we're slowly going to raise the block up by 40 degrees. And when we get to this angle, the box is going to start to slide. So if we draw a free body diagram, we're going to have a normal force that is perpendicular to our plank or to our ramp. Our weight of the box is going to be straight down, and since it's going to slide down, our force of friction, in this case static friction, is going to be up the ramp. Okay, so I'm going to put our positive x-axis going down the ramp and our y-axis going perpendicular. This is 40 degrees. And now that we have our free body diagram with all of our forces, we can start doing Newton's laws. So we want to sum up the forces in x and y. I always start with y when there is friction. So if we sum the forces up in the y direction, we have a normal force, and we have a negative y component of the weight, okay, and that's going to equal mass times the acceleration in the y direction. But since the block isn't coming off of the surface or going down into the ramp, we know the acceleration is 0. Okay, and now I'm going to substitute mg in for the weight, and to get the x component, or the y component, sorry, I want to use cosine since the y component is adjacent to this 40-degree angle. So I'm going to do cosine of theta, I'll just call it theta for now, and that's equal to 0. So if I solve for my normal force, which is what I typically want out of my y equation when there's friction, I get the normal force is equal to mg cosine of theta. And now if I move to that in blue, to the x direction, I have an x component of weight that is down the ramp, so in the positive x direction, and friction is going to be up the ramp in the negative x direction. And I'll set that equal to mass times acceleration. But since we're talking about static friction and we're raising the plane till just before the box starts to slide, our acceleration is going to be 0. So again, anytime we have static friction, we know that we can't be accelerating. If we were accelerating, then this would have to be kinetic friction. And so again, I'm going to plug in mg for the weight. And since the y component was cosine, we know the x component will be sine. It's also given by the opposite side of this right triangle. Okay. And minus mu s times n for our static friction force. And since we found the normal force in our y equation, we can substitute that in here. So we'll get mg sine theta minus mu s times our normal force, which is mg cosine theta equals 0. And now we can move this to the other side and get mg sine theta equals a positive mu s mg cosine theta. And we have an mg on both sides, so those are going to go away. We can divide those out. Okay, and we're looking for the coefficient of static friction, so we want to isolate mu s. So I'm going to divide by cosine, and what I get is sine theta over cosine theta equals mu s. And so this means that mu s is equal to tangent theta, since sine theta over cosine theta is just tangent. And since we know the angle of our plank, we can just plug in tangent of 40 degrees, and that will give us a coefficient of static friction of 0.84. So kind of a high number, but reasonable for static friction. So the next problem, we have a 2 kilogram textbook that is sliding at 3 meters per second when it encounters a rough ramp that is 25 degrees above horizontal. Find how far the textbook will slide up the ramp if the coefficient of kinetic friction is 0.3. So what's happening is we initially have this box that's sliding on a smooth surface, and then it encounters a ramp and starts to slide up, and the ramp is rough. So there's friction. Okay, so this is a rough ramp. And so it has its initial speed of 3 meters per second when it starts going up the ramp, but now that there's friction, it's going to slow down, and we want to figure out how far up the ramp this textbook slides. So as soon as it's on the ramp, we want to draw our free body diagram. That's when our forces start taking place, our friction forces. So we have a normal force that's up the ramp, and our weight is straight down. okay, towards the earth. And I'm going to put our x-axis up the ramp and y-axis perpendicular. So this is 25 degrees. Okay, and since we're sliding up the ramp, friction is going to be acting against us or down the ramp. And it's kinetic friction since we're moving. Now I'll start to sum the forces in each direction. So start with the y direction. Sum of the forces in y is equal to the normal force. It's in the positive y direction minus the y component of the weight, which is adjacent to this angle. So that will be cosine. So weight times cosine of 25 degrees. And that's equal to mass times acceleration. But since our block is not going into the ramp or coming off the ramp, it's not accelerating in the y direction, so this is 0. And I'm going to plug in mg for my weight. So mg cosine 25, and that equals 0. So I find my normal force is equal to mg cosine of 25. So now I can move on to the x direction. So I sum up the forces in x. I have a negative kinetic friction force. I also have an x component of weight that is negative. So that will be the weight times sine of 25 degrees. It's equal to mass times acceleration in x. Okay. And now I know I'm decelerating, so that's not equal to 0 in this case. And it should be equal to sign. And now I'm going to substitute in mu k times the normal force for friction and mg for my weight equal to mass times acceleration. And since I found the normal force in the y equation, now I can substitute it in here. Okay, so I get minus mu k times n, which is mg cosine of 25 degrees, minus mg sine of 25 degrees is equal to mass times acceleration in x. Here I can notice I have mass in every single term, so I can divide it through and get rid of it. And I've already have my acceleration solved for, so I just need to plug everything in. So minus 0.3 for my coefficient of kinetic friction times 9.8 meters per second squared cosine of 25 degrees minus 9.8 meters per second squared sine of 25. So you could factor out that g if you didn't want to put it in twice. And when you plug all this in, you should get minus 6.8 meters per second squared. Okay, and now in this case, since friction is our only force up the ramp and it is constant, well, it's not the only force. Since friction is constant and our weight is also constant, all of our net force causing this acceleration is constant. So this acceleration is constant. So I'll put constant since Fk and the weight are constant. Okay, so if all of your forces are constant, that means your acceleration is going to be constant. And that means we can use kinematic equations. So we know the acceleration, we know the initial velocity. We also know the final velocity because it's going to be 0 when it stops. So if I am looking for distance and I don't know anything about time, I need to use this kinematic equation. Okay, my final velocity is going to be 0 when it stops. Okay, and I solve for delta x, which is now going up the ramp and I get minus v naught x squared over 2ax, or minus my initial velocity of 3 meters per second squared over 2 times the acceleration I just found. And I get a total of 0.66 meters. Okay, in this last problem, we have a book weighing 30 newtons that is pushed against a wall with a force that is 20 degrees above horizontal. And we're asked to find the magnitude of this force if the book is to slide down at a constant speed and the coefficient of kinetic friction is 0.25. So as always, we're going to draw a free body diagram. So in this case, we have the weight that is straight down, as always. This time it's being pushed against a wall, which has a vertical surface. So if we're pushing to the left, it's going to be pushing out to the right, perpendicular to the surface. Okay, our applied force is up and to the left at an angle of 20 degrees above the horizontal. So just call this F. And then since the book is going to be sliding down, that means there's going to be friction fighting that in the opposite direction or up. So it's kind of weird to have friction up, but that is opposite the direction that we're moving. And I'm going to call to the left my positive x direction. Okay. So if I begin summing up the forces in x, I have a positive applied force, I'll just call that force F, minus the normal force, which is to the right, or in this case in my negative x direction. Set that equal to mass times acceleration, and the book's not moving left or right, it's only sliding down, so the acceleration is 0. So now I can write in I need to get the x component of this force, okay, this applied force. So that is going to be F times cosine, since the x component is adjacent to my angle. So F cosine of 20 degrees minus the normal force is equal to 0. Or my normal force is equal to this applied force times cosine of 20 degrees. Okay. Now I can move on to my y direction. If I sum up the forces in y, I have a positive y component of my applied force minus or plus kinetic friction plus my force of kinetic friction, and I have a negative weight, and that all equals mass times acceleration in the y direction. But since it is sliding down at a constant speed, that means it is not accelerating, so this is 0. If I substitute for Fy, this is F times sine of 20 degrees plus mu k times my normal force minus the weight, and that all equals 0. Okay, now I have my normal force, so I can plug it in into this equation. So this gives me F sine of 20 degrees plus mu k times my normal force, which is F cosine of 20 degrees minus my weight, which equals 0, or all of this equals 0. Now I want to factor out this force from both of these terms to isolate it. So I get F times, in parentheses, sine of 20 degrees plus mu k cosine of 20 degrees I'm going to move my weight over, so this equals the weight. And now if I solve for this force, I just need to divide both sides by this number. So my weight divided by sine of 20 degrees plus mu k cosine of 20 degrees. So plugging all of that in, I have 30 newtons for the weight, sine of 20 degrees plus a coefficient of kinetic friction of 0.25 times cosine of 20 degrees and this gives me an answer of 52 newtons.